The goals in this chapter 6 are to better understand the safety hazards. I introduced some of the concepts of safety in the introduction, but we're going to spend more time in this section talking about what can happen with an overexposure to ultraviolet, general safety measures in addition to UV, and then the safety from airborne contaminants. It's important for you to be able to determine what level of germicidal UV is safe and how best to control potential UV hazards. So the objectives for this chapter 6 is to bring you up to a level so that you will be able to describe to users the importance of germicidal safety requirements. You'll be able to describe to users the signs and symptoms of accidental overexposure and be able to understand the relationship between UV total exposure, exposure rate, and time, and also be able to calculate the maximum UV exposure of room occupants. This is why germicidal UV certification is critical, because improper installation and service of germicidal luminaires can cause injuries. So safe expert installation is really critical. And your expertise in lighting installation, maintenance, and service provides the ideal background to learn about germicidal UV installation, safety, and maintenance. Germicidal UV has a long history, went largely into obscurity except to control tuberculosis. It's still in widespread use in some special locations in a number of countries around the world. Now, accidental eye exposures because of faulty installations have led to removal in some locations, where, for example, the installers didn't understand the objective, the design, and directed the UV into the lower occupied areas of the room, and people were injured. And this led officials to simply remove this very effective risk control technology. But it still is used in TB hospitals, and it was used during the COVID-19 pandemic in a number of locations. The accident experience are shown here, where the upper room device was installed without a recognition that there were areas in the occupied space which were elevated, such as in this stairwell. The fixture was mounted properly if it had been in a normal room without any elevated areas. So you always want to be sure that the elevation of the disinfection zone is covering all of the space and not just near the fixture. Some fixtures have been installed upside down. I remember one case where the fixtures were mounted upside down and directed downward, and when we asked the installer, who had not really understood the real design, why it was installed upside down, he said that he didn't see why it should be illuminating this in the ceiling. Since people were down below, it needed to treat the air down where people were occupied. So this is an example of why we have to have properly trained installers. Think 1.8 meters above the floor, or about 6 feet, would be the lowest area where you have a germicidal disinfection zone in the upper room. luminaire directed downward might be installed by a novice, but there are some companies who have designed their luminaire so it can't be directed downward. So how do we know what level is safe for the people in the lower room, in the occupied spaces? And fundamentally, I can tell you that there have been decades of research to reveal the most barely detectable changes in surface cells of the eye and skin. And safety limits have been established by health experts who examined all of the available research studies, considered the typical exposure that we all receive from sunlight and so forth, knowing that levels in sunlight are dangerous. And to give you a perspective, the exposure limits we have today can be exceeded in a summer day, in the middle of the day, in about 10 minutes for most people. So these are conservative limits, and we really do consider them safe. So what group sets these guidelines? They're both national and international organizations, and some governments have issued human exposure guidelines to promote safety. The ACGIH, NIOSH, ICNIRP, ISO, IEC are all organizations that have published exposure guidelines to limit needless exposure to UV. ACGIH stands for the American Conference of Governmental Industrial Hygienists. ICNIRP stands for the International Commission on Non-Ionizing Radiation Protection, and ISO is the International Standards Organization. IEC stands for the International Electrotechnical Commission. And most of these guidelines relate to harmful sunlight exposures, which is, of course, the UVB in sunlight. UVC isn't present in sunlight, but it's considered much safer in terms of delayed effects. It's just a whole lot more effective in its germicidal action against microbes. So one of the most widely used professional exposure guidelines is seen there on the right, the ACGIH threshold limit value book. And it has limits for carbon monoxide and benzene and all sorts of complex chemicals and other physical agents such as noise and magnetic fields or heat stress. But it does have exposure limits for ultraviolet C. I should note that the TLV is actually a registered trademark of this American Conference of Governmental Industrial Hygienists. The ACGH TLVs are limits for many different work-related airborne contaminants, including ozone and benzene, as I mentioned, and heat stress and UV and infrared. But the TLV for ultraviolet, as we see on the right panel there, has this fundamental formula that's important to write down. And this is that the effective radiant exposure is equal to the effective irradiance times time. Now, notice that I've used this term effective, and we see the little subscript there next to H for radiant exposure and E for irradiance. That simply means that it varies with wavelength depending upon how risky that wavelength is to the eye and skin. And the daily exposure limit is 3 millijoules per square centimeter effective. That means if you have an effective irradiance of 0.1 microwatt per square centimeter, in 30,000 seconds, it's going to achieve 3 millijoules per square centimeter. for continuous irradiation. But nobody is really exposed to the same level constantly. And that's why we have to consider a time weighting of the exposure. Now, let's do a simple calculation for a typical 254 nanometer low pressure mercury lamp, the traditional germicidal lamp that's used in upper room safety, upper room installations. The actual TLV is 3 millijoules effective. However, the effective irradiance is different than what a lot of meters will measure. And that is that an absolute irradiance is not 0.1 microwatt per square centimeter over 30,000 seconds. It's really 0.2 microwatts per square centimeters, because the weighting factor S lambda is 0.5 for 254 nanometers. So that's an example of how the typically measured irradiance is different than the effective irradiance. The only wavelength which is precisely the same as the absolute irradiance is 270 nanometers. That's the peak of the hazard action spectrum for irritating the eye, the cornea of the eye. And that's where S of lambda is a value of 1.0. So the ACGH limits can seem complicated, certainly if you start with an unknown type of lamp source with many different wavelengths. But for the typical germicidal lamps that are widely used, it does work out to be something fairly simple. Now, it also turns out that some safety meters are direct reading, so it automatically does this adjustment for you. So you want to be sure whether your instrument is calibrated to read the safety limit for your wavelength or whether it's just an absolute measure of irradiance. The instructions for your meter should tell you that. Remember then that at 270 nanometers, S of lambda is equal to 1.0, the maximum value. For the mercury 254 nanometer wavelength, S of lambda is equal to 0.5. And for the krypton chloride wavelength of 222 nanometers, S of lambda is equal to 0.02. That means that you can have a great deal more radiant power in the room and use it safely if you were using 222 nanometer krypton chloride filtered lamps. The higher the value of S lambda, the more hazardous. So here's an example of the action spectrum. Human exposure limits are going to vary with wavelength according to the action spectrum. Now, I've actually plotted 3 different wavelengths on here, and I want to explain that the vertical scale is referred to as logarithmic. In other words, each one of the little intervals here on the left-hand ordinate is a factor of 10. The top line being 1.0 or 10 to the 0, and then the next line below 10 to the minus 1 is 0.1 or 10%, and then 10 to the minus 2 is 1%, 10 to the minus 3 is 0.1%, and 10 to the minus 4 is 0.01%. So that's a huge change as a function of wavelength, particularly as we move into the UVB. And there are 3 action spectrum here. The solid line is the ACGH threshold limit value for UV. The dashed line is the standardized CIE erythema or sunburn action spectrum that's used in the derivation of the UV index, if you pay attention to that in the weather report. And the CIE NMSC is the non-melanoma skin cancer action spectrum. And this is really important to be able to explain to users, because the relative risk for skin cancer by wavelength peaks around 300 nanometers in UVB. And you can see how this is dramatically limited to just the UVB band. And it has values down to less than 1% efficacy for causing damage to DNA that could lead to skin cancer, as shown here in this dotted line in the UVC. So at 254, the risk is vastly less than sunlight, centered at 300 nanometers in the UVB. Remember, this shows again that at 254, the value is about 0.5 for S lambda, and it's 1.0 at 270. Human exposure limits then vary with wavelength, and this is the fancy equation that would be used if you had an unusual new type of lamp. We don't have to worry about doing that type of calculation, but a lamp company or a lamp manufacturer might have to do it if they introduce, say, for example, a new LED that operates in the ultraviolet. They would need to weight the spectral distribution of the lamp, E of lambda, by the weighting factor, S of lambda, for every little interval as it goes across the spectrum. And most LEDs, for example, have a bandwidth of, for example, 15 or 20 nanometers. So it would have to cover that particular area to come up with what the effective irradiance for that lamp would be. That would be of concern. So remember then, in red there, the effective radiant exposure is 3 millijoules per square centimeter. In some books, you'll see 30 joules per square meter. That's the same value. It's just averaged over a huge area compared to a square centimeter. The limit is for daily exposure, includes multiple exposures. And this is where we have to introduce the term time-weighted average. Time-weighted average is used always with threshold limit values, whether we're talking about some chemical exposures or, for example, in this case, ultraviolet exposure, because you're seldom in the exact same location in the room. You may not be in the room for very long. And so the time-weighted average sums up how long you're at a particular spot. Now, we've come up with some worst-case guidelines that you can apply when you're not sure of the occupancy times and so forth in a given site. And the most conservative assumption is to stay below the time-weighted average of 0.2 microwatts per square centimeter at least spaces below 1.8 meters above the floor. And don't forget, this is the highest point in the floor, not some shallow area. So I need to point out that in 2022, HGH increased its TLVs for the eyes and the skin, and these were definitely raised at wavelengths below 250s for the eye. It introduced a separate limit for the skin, but normally we have to limit the exposures to that which would be safe for the eye. So here's some examples. If we had nearly monochromatic single wavelength lamps, such as a 222 nanometer krypton chloride excimer lamp, these are the exact values of S of lambda for the eye and skin at 222. You see they're very small numbers, which allows much higher exposures in terms of microjoules per square centimeter, which we see on the right panel. So at 254, as we've said over and over again, the S lambda is 0.5. Now at 265 nanometers, which is one popular UV LED, it's 0.81, or if you had an LED at 270, it would be the most effective against the airborne viruses or bacteria, probably, but it would be have the lowest permissible exposure limit. So how do we convert those effective radiant exposure values, which would be the limit for a given wavelength, to the worst case 8-hour dose rates? Well, we have to divide that radiant exposure TLV by 30,000 seconds to get microwatts per square centimeter. The 8-hour TLV then is, in terms of the worst case irradiance for 222 would be 5.58 microwatts per square centimeter for the eye and 16 for the skin. The 254, though, is less than a microwatt per square centimeter, 0.21 for the eye, 0.35 microwatts per square centimeter for the skin. 265, even lower at 0.13 microwatts per square centimeter for the eye, 0.35 for the skin. And finally, 270, S lambda is equal to 1, so that's the lowest limits you'll find, 0.1 microwatt per square centimeter for the eye over 8 hours, and 0.35 microwatts per square centimeter for the skin, according to the ACGH 2022 limits. So how do we apply these limits for upper room germicidal UV? Now, something we haven't mentioned is that when you make a measurement to determine whether you're exceeding a threshold limit value, you really need to only measure over an 80-degree cone angle. And some manufacturers of safety meters give you a little accessory that limits the exposure to 80 degrees. If you don't have that cone angle, you can build something out of a cardboard tube, or simply be overly conservative and don't put the cone angle on there. Now, for high efficacy, for upper room irradiance, you would normally want levels of the order of 400 microwatts per square centimeter, which is far, far above the 10 microwatt per square centimeter limit. That means that the lower room ACGH TLV has to stay below 6 millijoules per square centimeter for an 8-hour period, or a time-weighted average of 0.2 microwatts per square centimeter. So remember that the exposure limit, the TLV, is a limiting value for the eyes. The skin limit, according to ACGH, is really only a goal, at least for sunlight, because it was considering the more sensitive individuals. But the limit for the skin in the UVC was also raised a little bit in 22, but not nearly as much at 254 as at far UV wavelengths like 222, where the increase was substantial based upon the biological effect studies that were considered at that time. So safety in your installation is going to be ensured by you checking the UVC irradiance in the occupied zone. And this is generally read on a safety meter in microwatts per square centimeter, or even milliwatts per square centimeter. So what are the exact effects that would happen if you had overexposure? Overexposure of the skin produces a slight reddening of the skin, which is technically termed an erythema. And this erythema is a mild sunburn-like effect, resulting quite often more in an itchiness of the skin and slight pinkishness in some people's skins when one is exposed to twice or even 3 times above the safety limit. However, I want to emphasize, with some of these lamps, it's possible to have an accidental exposure far above that. And there have been some more serious injuries to technicians working unprotected for hours, reaching exposures above 100 times the safety limit. And the severity was really due to the small amount of the more penetrating UVB from a mercury lamp. So you want to be really careful when you're working with these lamps not to have a condition where someone is unaware that the lamp is emitting UV. They may think it's just like another little blue light lamp or something, because there is some visible light coming out from even the mercury lamp. And so as an example, one might encounter a mild reddening and itching of the skin after failure to wear gloves when operating a 254 nanometer lamp. And an overexposure during a 1-minute emission measurement of 500 microwatts per square centimeter at a foot, 30 centimeters from the lamp. So when you're making measurements for efficacy to see if it's really a good installation, it's really going to disinfect, you may have to raise your hand up into the treatment zone. So you need to wear protective sleeves and protective gloves for any skin that might be exposed up in the upper room. Now let's go into a little more detail about the skin. And the figure here shows a diagram of the different layers of the skin. The outermost layer of the skin is the stratum corneum. That's that very thin layer on the very top that's painted in orange. And then the living cells is the epidermis. The epidermal cells are created daily down at the basal layer. That's that line between the epidermis and the dermis. And those cells have the important DNA, and those are the germinative cells that are producing new cells. They're dividing constantly. So it's really important that UV rays don't reach down to that basal layer. The cells themselves spend a couple of weeks gradually moving up layer to layer up towards towards the top of the epidermis, and eventually die and form what we call the stratum corneum. Now, some wavelengths down around 200 or 222 barely penetrate the thin stratum corneum and are unable to significantly damage the surface cells of the epidermis which are about to die anyway. 254, though, penetrates a little bit more deeply, but generally not as far as the basal layer. But 300 nanometers in the peak of the UVB, the peak of the photocarcinogenesis action spectrum, the skin cancer action spectrum, that you see does reach down to those germinative cells and the basal layer of the epidermis. So this is where the cells divide, and this is where you have that theoretical risk of skin cancer. Now, 222 nanometers was introduced in the last decade or so, and it was introduced because it seemed to be so much safer, and based upon all studies so far, it certainly seems to be far, far safer, because most of the energy doesn't even enter into the epidermis. And if it does, it's just the most surface cells that are about to die anyway to become the stratum corneum. Skin cancer, then, is a real risk for UVB, but not for UVC because of the shallow penetration depths and repeated overexposures. There are usually very rare. Even less potential for damage to skin tissue from exposure to the shortest UVC wavelengths, the so-called far UVC wavelength. So there have been efforts to draw an action spectrum for delayed effects like skin cancer. And it's important that people recognize that skin cancer is really largely caused by excessive exposure to sunlight, and most specifically the UVB in sunlight, which is very intense in the summer compared to what it is in the winter. It's 10 times more present in summer months than it is in winter. The non-melanoma skin cancer action spectrum here is plotted on linear paper, and as you can see, it's pretty well limited exactly to the UVB. So the judgment of experts is that UVB is the bad actor. That's the wavelengths from 280 to 315 nanometer, but germicidal UVC is not a realistic concern when people stay below the exposure limits for UVC. Why? Because the UV photons don't penetrate to the germinative cells in the skin. Now let's examine what happens with the eye. The eye also is exposed to the UVB in sunlight, but it's exposed far less than the skin because the eye is normally aimed slightly downward when you're outside, and the upper lid and the brow ridge block an awful lot of UVC from overhead skylight. The UVC is completely absorbed in the cornea. That's the outer window of your eye. And the eyes protect the UV and sunlight because of the orientation and the upper lid acting as a sunshade. And the eyes constantly shed the surface cells from the cornea that are damaged by sunlight UV. And there is a rapid turnover of those surface cells anyway. When you wake up in the morning and you wipe your eyes and you have that stuff, it's not sand from Mr. Sandman. It's actually dead cornea and conjunctiva cells that are sloughed off overnight in order to give you a very nice, clear vision and a transparent cornea in the morning. The figure on the left shows you that the structure of the cornea with a very thin layer of epithelial cells, which are constantly being generated, just like the epithelium of the, or epidermis of the skin. And the tough part of the cornea is known as the stroma, and this is largely collagen fibers and so forth, and it's very tough. Very little UV gets all the way to the stroma, 270 nanometers to some extent, certainly. 254 slightly into the stroma, and 222 is just all absorbed in the outermost cells of the corneal epithelium. I want to emphasize that the skin and the eyes are designed to deal with a bath of ultraviolet photons that are coming from sunlight, or we wouldn't survive. And there's constant repair of damaged DNA in the skin and the cornea and the epidermis and so forth. So that the eyes are constantly shedding the surface cells. They have a limited lifetime of a couple of days from when they reach the surface and then are sloughed off. So we don't have a memory of what's happened to the surface because it's not affecting the germinative cells of the cornea. So accidental overexposure can be serious in terms of pain and acute effects, but these are transient. They generally disappear within a day or two. And they are not directly related to any risk for delayed effects compared to UVB. The sensation of sand in your eyes is normally gone after a day or two. It's very unfortunate, and I hope that in your work you'll never have to experience, because it can be fairly painful, and at least for the eyes. It's not painful for a slight overexposure of the skin. That normally disappears in a couple of days, compared to a severe sunburn, which can last for a week or two from sunlight UVB. So I want to emphasize that most accidental overexposures to UVC, germicidal UV, occur from faulty installations, with baffles and mercury lamp fixtures aimed slightly downward rather than slightly upward. So competent installation and maintenance is important. We say an expert installing a UV fixtures. That's a louvered fixture with which has a baffle so that the UV from the mercury lamp inside is directed upward, and the individual knows to install it properly. There's also a need to clean and maintain these lamps. So it's not just a matter of installing and forgetting. You need to be maintaining them, replacing the lamps, and in each case, you need to be doing this work with the electrical supply to the lamps off, so that we see a final installation in this waiting room in a hospital or clinic where we have the UV fixtures suspended from the ceiling. And I want you to see that they're ceiling fans. So the ceiling fans are circulating air in the vertical direction to constantly mix the air that has been where the virus or bacteria have been inactivated, and mix the clean air with any contaminated air. to reduce the concentration and the breathing zone of the people in that room. So let's go over again about what can happen then from excessive overexposures. This is normally about tenfold above the safety limits or the TLVs, because there's some UVB emission from the 254 nanometer UVC lamps, about 10%, whereas 90% of the energy is in the UVC. A very excessive overexposure, more than 10 times of the TLV, can result in a more severe photokeratitis and a deeper reddening of the skin that will be more like a real sunburn. So under these conditions, the recovery from the erythema or the photokeratitis may take even more than 2 days. Long-term effects, delayed effects, are still not expected unless this even happens over and over, or at very, very severe overexposures, like 100-fold above the limit. So I want to also just spend a moment and talk about far UVC and why proponents of the far UVC lamps claim far more safety with equal or better efficacy. And the reason is that at wavelengths less than 235 nanometers, the penetration into skin and eye tissues is so much more shallow, because almost all proteins and main building block of tissue are highly absorbing at wavelengths less than 235 nanometers. So there's a minimum potential for damage to human tissues from far UVC for the same irradiance levels, same dose rates. This offers the potential for whole room applications where you can actually deliver the UVC from overhead luminaires, directed the energy straight into the occupied spaces. So this offers a potential for significant improvements in disinfection efficacy compared to the conventional mercury lamp UVC. The tear layer absorbs a substantial amount of the far UVC energy, but also the penetration depth is so shallow that the safety limits are quite a bit higher at those shorter wavelengths than at 254. I mentioned that in 2022, the ACGIH revised their limits in the far UVC particularly, and you'll see the changes there. The exposure limit is plotted in the left panel as a function of wavelength on a logarithmic scale, and the S lambda curves, or the spectral weighting curves, are shown in the right-hand figure. They're both used in deriving the limits. The S lambda relative spectral effectiveness plotted on the right, when multiplied by the measured irradiance, gives you the exposure limit over on the left. And as you can see, the 222 nanometer limits are substantially higher. The 254 limit for the skin, slightly higher, but the eye limit for 254 remain the same. So it's really interesting when you start to study the UV hazards to the eye of how well the eyes are adapted to the outdoor UV in sunlight. Normally, the most intense UV falling on Earth is when the sun is very, very high in the sky, which only happens in the summertime in the late spring and the early summer, when the sun can get right above you practically. And under this condition, your shoulders and the top of your ears and the tip of your nose are getting the highest exposure. But the cornea is hardly being exposed at all, to just a few percent of what your top of your head would be exposed to. And this, what a lot of people don't realize is that the upper lid actually acts as a sunshade, and it moves up and down depending upon how bright the sky is. So indoors, your upper limit of viewing is about 45 degrees if you're looking straight. And outdoors, it may go down to just 15 degrees above the horizon because of this protective mechanism. And of course, we've already stated that the cells of the surface of the skin and the eye have a very short lifetime, and they're constantly being sloughed off in order to protect the deeper, more important layers that are responsible for germinating new cells. So when we have an excessive exposure outdoors, it's generally if we have a very reflective surface like snow. And you may have heard of snow blindness, which occurs in the early spring when the sun starts to rise and we get a good dose reflected off of snow. Another place where we have experience with photokeratitis is welder's flash. And that's because arc welding produces a lot of UVC, and the welder has to be well protected, not only for the eyes, but also for the skin. And they wear a very protective welding helmet for that situations. So the 254 nanometer lamp is exposing someone to 100 microwatts per square centimeter for 3 minutes. And that's way above the threshold limit value. And 3 minutes would be 180 seconds. So 180 seconds times 100 microwatts per square centimeter gives you a level that exceeds the threshold limit value. And as a result, the person is going to note a painful irritation like sand in the eyes in 5 or 10 hours after that exposure. I mentioned earlier that the field of view is specified in the TLV, that if you have a safety meter, in theory, you should limit the field of view to 80 degrees. And this is because the lids are only open to give you something on that order from overhead and direct. And also when UV strikes the skin or the eye at a grazing angle, at an angle outside of that 80-degree field of view, more is reflected and more is absorbed superficially. So that's the basis for that field of view hood on a safety meter. I've mentioned more than once the concept of time-weighted averaging, and the time-weighted averaging is a very important concept. It's particularly important if you have a UV fixture that doesn't run continuously but goes on with some short periods. This has been typical of a number of excimer lamp germicidal fixtures, where it might be on for a minute, then off for several minutes, or something like that. And in which case, you don't have to keep the exposure in the occupied space down below the peak. It's got to be the average irradiance. And this illustrates the concept of a time-weighted average. whereas you have a certain maximal value periodically, but the pulse repetition frequency is controlled to stay below a safe level at a particular measurement distance. You can also apply time-weighted averaging if occupancy factors are known. And this has been done, for example, in restaurants or in places where people are not going to be occupied for any length of time. And the illustration here for upper room germicidal is where, for example, the number of situations where somebody is going to be standing is considered always less than an hour in any one day. So one could have a higher dose rate above maybe 4 feet, 4.5 feet, 1.3 meters above the floor, as this conference room setup was established. But you have to be confident that you're not going to have some unusual situation where the people are forced to be standing for very long periods of time. Not likely, but we have seen installations where the installer was able to take advantage of well-known occupancy factors and therefore have a slightly higher level below 6 feet or below 1.8 meters. Now, I'm often asked whether there are some individuals who are more sensitive to UVC. And there is a term that dermatologists or skin doctors refer to as photosensitivity. And this is an effect that can be characteristic of someone with a certain photosensitizing disease, or they're taking a medication. For example, there are some common medications such as tetracycline, an antibiotic, which is a photosensitizer, and lime juice and some foods can make you slightly more photosensitive. But this is really referring to a photosensitive reaction from UVA wavelengths, from long wave ultraviolet, not the shortwave germicidal UVC. And I don't want to go into all the technical details of why, but these effects are pretty well limited to UVA, and to a lesser extent UVB, but it's certainly not expected not to be a problem for UVC. Now, there may be some individuals with unusually thin stratum corneum. After you shave, you remove a little bit of your stratum corneum, but it still is not going to be a very significant effect as long as you're working only in the far UVC. The UV erythema varies a great deal with skin phototypes. In other words, people with heavy skin pigmentation have a higher threshold for skin reddening than a very pale light skin. And therefore, the skin cancer risks vary a great deal by individuals if we're talking about UVB and sunlight. This type of individual sensitivity is not expected to be significant down in the UVC. The feasibility of implementing upper room germicidal mercury lamp then depends on your safety assessment. Even before you install, you need to be sure that the ceiling height is really sufficient so that you'd have an upper room volume adequate for having an effective installation. So you need to know the upper room volume, the physical dimensions, the functional considerations, the limitations due to activity in the space. For example, if there are gymnastics or basketball playing in a gym, you might have to be concerned about even higher elevations than 6 feet above the floor. Don't forget, there might be some elevated spaces like speaker podiums and so on. So take those into account when you're setting up your lamps. Let's consider a conference room with a 10-foot ceiling height, 3 meters ceiling height. The UVC luminaire is normally positioned above 7 feet, and these are installed so that a suspected chandelier or a ceiling-mounted television set doesn't reflect UV into the occupied spaces. And that's particularly common these days with a lot of these different projector screens and other gadgets up in the ceiling area. So you need to position your germicidal lamp fixtures or UV luminaires so that they're not aimed directly at any of these particular items suspended from the ceiling or up in the high wall area. You also need to position those in locations where there's ventilation vents so that you're going to get good air movement in the area being most irradiated in the upper space. Here's an example of a technician cleaning a germicidal lamp in a medical facility in a TB ward. And that's really very interesting. And you'll learn more about that in another section of this course. But when you're doing maintenance, such as cleaning, be sure to turn off the lamp. You certainly know if the lamp is operating because you can see the glow of the discharge tube. You need to wear a protective face shield. You need to wear UV protective clothes, gloves, and if you cannot turn the lamp off. But the most important approach is just be sure that the lamp is turned off while you're doing this. You also want to be sure to confirm that it's the proper lamp. Unfortunately, there have been cases where people have taken a germicidal lamp and put it in an insect attractant lamp, and people got injured from misuse of the germicidal lamp. But you also need to be sure that your lamp is actually emitting in the UVC, and you will know that if you do a quick measurement check to make sure that you have an effective irradiance in the upper room. It goes without saying that in dealing with a fragile glass envelope lamp, you don't want to break it. So you don't want to have shards of glass flying around. Here's a photograph of what not to do. And it's surprising that this actually could be photographed. This fellow looks like an experienced maintenance technician, but it's well to remember that OSHA tells us that one of the most common occupational accidents results from falls from ladders. So please make sure that you have appropriate ladders and follow the ladder safety measures. What personal protective equipment or PPE do you require? I mentioned them before, but you need to protect the skin and the eyes when the lamps are on and when you are present in an active emission zone. You need to wear a full face shield and not just goggles because your skin can be exposed. And you need to cover your skin with gloves and industrial type clothing, thick, heavy duty clothing. And you need to wear PPE when lamps are on. But again, read what we have in red there. Never perform maintenance with the lamps on. But in any case, during measurements in the upper room or in a duct, full PPE is required. And during safety measurements, goggles may suffice. But remember, it's easy to get overexposed if you're not aware of the time and you do a number of installations that day or checks. By the way, don't use sunscreens. These are really not reliable. Few people put them on adequately, and it's not considered a good occupational protector. Again, I'll go back to some of the newer excimer lamps, the krypton chloride lamps, just so you're familiar with that when you see them, if indeed you're not installing them quite a bit. These are normally emitting at about 222 nanometer wavelength. There's a secondary peak around 258 nanometers, and there's some UVB coming out of these lamps unless they're filtered. So it's important, if you're using krypton chloride excimer lamps, please make sure that it has an optical safety filter to block the longer, more penetrating wavelengths of UVC and blocking the UVB as well. There are other solid state sources or UV LEDs in development, and it's not clear that they won't pose another risk of not emitting enough visible light so you can see that they're on. Even the krypton chloride lamps, way down at 222 nanometers, have enough very weak emissions in the visible that you can see when the lamp is on. And although the krypton chloride lamps are vastly safer than 254, they should only be installed on the ceiling or very high to minimize direct exposure. You don't want to have them on the wall aimed straight at occupants. Then you might run into some complaints, because at high levels, high dose rates, you can actually sort of sense a little bit of dry eye. You have to blink more often. So you don't want to be in that condition. Another issue that lots of people ask about is the production of ozone. And as you get to shorter and shorter wavelengths, particularly below 240 nanometers, there will be some ozone produced. And this airborne contaminant has a symbol of O with a little 3. It's very highly reactive chemical gas. And as the wavelength decreases, there's more ozone produced. This is normally not a problem for low pressure ozone-free mercury lamps. And you want to check, there are some low pressure mercury lamps that are intended to produce ozone for some chemical reactions and use where there's no one who might be exposed. And these do not have the far UVC blocking envelope because there's a very strong emission line at 185 nanometers in the far UVC, even beyond far UVC, and it efficiently produces a lot of ozone. Basically, I can tell you this, that if you have a couple of air changes an hour, the production of ozone should not be a significant concern. The normal room ventilation and also furnishings quickly dissipate the ozone. And the ACGH TLV for an 8-hour exposure to ozone is 50 parts per billion, 50 ppb in air for heavy work, but 100 parts per billion in air for very light work, for example, in an office. So there are other groups that recommend a lower limit of 50 parts per billion for indoor air in any case. Whatever the case, it's unlikely that you're going to have significant buildup of ozone, provided you have some ventilation. That said, you need to think twice before trying to use 222 nanometer krypton chloride lamps in a room where there's no forced air ventilation. That could be a problem. If you smell it, it's probably exceeding the limits for constant 8-hour exposure. So let's summarize the key points of this section. Photokeratitis, or welder's flash or snow blindness, it has a symptom of sand in the eyes. The cornea is the most sensitive tissue, and conjunctiva, which covers the white of the eyes, shows the signs of irritation of the eye surface. The good news is that it's transient. As far as we know, unless you do it over and over and over again, there's no chronic delayed effects to worry about. And in the case of the skin, erythema or reddening of the skin can be severe if there's a lot of penetrating UVB rays, but is normally mild if you're really dealing only with UVC because of its very superficial penetration into the skin. And accidental exposures of the skin and eyes should not pose any significant risk of skin cancer unless the exposure is vastly above the permissible limit, because the UVB, which is present in all low pressure mercury lamps, can become significant when you're exceeding, for example, 10 times the TLV. And it's recognized that it's UVB that is the cause of most skin cancers. UVC is heavily absorbed in superficial epidermis and stratum corneum, and it's not considered a realistic risk for skin cancer. Our key conclusions, our most important takeaways are: number one, germicidal UVC is a valuable countermeasure against aerosolized microbial infections. The need for trained installation and maintenance technicians is very clear. It's important for UVC installation and maintenance technicians to be able to explain safety to users. We don't want unwarranted fears about an installation after it's been installed, because the users don't understand the real safety. And far UVC emissions can be safe for whole room irradiation, and further development is undergoing for that application. The key elements in the germicidal UV safety program are risk communication elements and ask the University Maryland Safety Office for help if you need further clarifications. Thank you. I might just say here that there are quite a few safety standards if you are a designer of installations and so forth. Several from Underwriters Lab or UL for germicidal systems, and standards for electrostatic air cleaners. And there's also an important point that there should be no ozone emissions from air cleaners. This is where you have a UV lamp inside a console unit, which blows air through a very effective filter, but also irradiates the air inside this unit with ultraviolet. The Illuminating Engineering Society, the IES, has recommended practice 27.1 on photobiological safety for lamps and lamp systems, general requirements, and it has requirements for UVC as well. And the IES also has an extremely useful booklet called Recommended Practice for Germicidal Irradiation. You can download that from the IES website at a modest price. Thank you.